Let's look at an example problem where we try to determine the rate law from experimental data. So we're going to use a very general reaction here. A moles of A plus B moles of B plus C moles of C. We have three reactants. Go to D moles of D plus E moles of E. Okay, recall, since we have three reactants, we now need to run four experiments. Always one more experiment than number of reactants that we have. And so we'll start out with some nice numbers, 0.1 molar for the concentration of A, B, and C, all 0.1 molar, very pleasant, nice math. And a rate of 1.1 times 10 to the negative fourth. Please note these are made up values here. In the lab, it's very tough to get exactly 0.1 molar. You can work on it, but then your rate laws coming out with nice numbers is very difficult. These are idealized numbers, not what you might get in the lab. Okay, but we have got these nice numbers here. Second reaction, note we're going to increase the concentration of A by a factor of 2, but leave the other two the same. For 3, we're going to take the concentration of A back down to 0.1 molar and increase the concentration of B by a factor of 2. C stays the same. And in 4, we're going to keep concentration of A at 0.1, B at 0.1, and raise the concentration of C to 0.3, 3 times the normal concentration. Okay, and when we do that, let's say we got these nice numbers here. So the question now is, what's the rate law, and can we calculate the rate constant? Well, the form of the rate law, we can just write that down right away. Rate equals K times the concentration of A to some power X times the concentration of B to some power Y times the concentration of C to some power Z. That's just the form of the rate law. When we're asking what is the rate law, what we're really saying is what's X, Y, and Z. What are those numbers? Well, let's look what happened. So let's compare reaction 1 and 2. When we compare reaction 1 and 2, note we doubled the concentration of A. Note whenever you're comparing, excuse me, whenever you're comparing two reactions to see what happened, make sure that only one number is different in those two reactions. Here, this number, first number, concentration of A is different, but concentration of B and C remain the same. You can only change one variable. So we doubled the concentration of A. What happened to the rate? Well, we multiplied the concentration of A by 2, but what do we have to do to 1.1 times 10 to the negative fourth to get 1.1 times 10 to the negative fourth? We have to multiply that by 1. So we multiplied the concentration of A times 2, multiplied the rate by 1, so 2 to the x power equals 1. If you remember from college algebra, and I bet you didn't, how does we get anything to the x power equal 1? Well, it turns out anything to the 0 power equals 1. 2 to the 0 power equals 1, 10 to the 0 power, 1,579,000 to the 0 power equals 1. So, I doubt you thought you'd ever use that little tidbit of knowledge, but here we go. X equals 0 here. So that means we have A to the 0 power, which means this whole term is just 1, which means that term is not really in the rate law. Just we're multiplying everything else by 1. So the concentration of A does not affect the rate of the reaction. Okay. Let us compare reaction 1 and 3. When we compare 1 and 3, concentration of A is the same, concentration of B is doubled, concentration of C is the same. So we doubled the concentration of B, but what happened to the rate between 1 and 3? 1 times 1.1 times 10 negative fourth times what equals 4.4 times 10 negative fourth? Well, multiplied it by 4 to get 4.4. We multiplied this rate by 1. So doubling the concentration of B gave us 4 times the rate. 2 to the y equals 4, y equals 2. What this means is this reaction is second order in B. Reactant B affects the rate to the squared power. All right, now let's look at 1 and 4. Compare 1 and 4 here, and we see concentration of A is the same, concentration of B is the same, concentration of C tripled. So 3 to some power Z, well, what happened to the rate? The rate was also multiplied by 3, comparing 1 and 4. The rate was multiplied by 3. 3 to some power Z equals 3, Z equals 1. So this reaction is first order in C. Note, why didn't we compare, say, reaction 2 and 3? Well, because this value changed and that value changed. We had two numbers changing, so we would never compare those two. We only change one variable at a time. But now that we've done that, we now can write the actual rate law, because we know the rate equals K times the concentration of A to the 0 power, so we're not even write that in. Rate equals K times the concentration of B to the 2nd power times the concentration of C to the 1st power. And recall, we usually don't include to the 1st power. We don't write down to the 1st power. So the result is our rate law is rate times K. Our rate law is rate equals K times the concentration of B to the 2nd power times the concentration of C. Note this is third order overall, because 2 plus 1 is 3, third order overall. And then how would you calculate the rate constant? Well, plug in one of the rates from the first reaction, from one of the reactions, and it didn't matter which of those 4 reactions on the previous page you used. First one would be nice. Put in the rate there, which is 1.1 times 10 to the minus 4th meters per second. Our concentration of B was 0.1 molar, C was 0.1 molar, and solve that for K. And when you do, you find K equals 1.1 times 10 to the minus 1 molar to the minus 2 seconds to the minus 1. Watch out, the third order rate laws have kind of funky units. All right, well, let's continue on now. Now we're going to look at the concentration of reactant with time. Another way of saying this, we're going to look at the integrated rate laws, the integrated rate equations. Okay, we'll start with first order reactions, and so we're going to spend a little bit of time here on these first order reactions, where the reaction depends on the reactant concentration to the 1st power. So here's an example. A goes to product. Some reagent A forms some product. Recall, if we're measuring the rate of the reaction, if we're looking at the rate of the reaction, we want to find out how fast it goes, we have to measure the concentration of A, the change in concentration of A with change in time. Since it's the reactant, it's negative. So the rate of the reaction will equal negative change in concentration A with change in time. But we also remember the rate law for this reaction is rate equals K times the concentration of A. Now you might be saying, wait, shouldn't this be to the X power? Yes, but since we already have said this is a first order reaction, the concentration of reactant to the 1st power, we have already determined that this is a 1 here. So the rate equals K times the concentration of A. Well, this rate that we measured by running the reaction and this rate have to be the same rate. Therefore, negative change in concentration of A with change in time equals K times the concentration of A. Now these are the integrated rate laws, which means we do a little calculus on this equation, and voila, we get the integrated rate equation for a first order reaction. Natural log of the concentration of A naught divided by the concentration of A equals KT. Now let's look at all these things. Natural log, well, that's just natural log. A naught, that means the concentration of A at the beginning of the reaction. Well, technically at any time 0. You said, okay, I'm going to call time 0 where I start monitoring right now. That's our A naught when we start monitoring the time. Divided by concentration of A, that's the concentration of A at time t. You will see a lot of books have concentration of A with a little t under it. So concentration of A naught is our initial concentration. Concentration of A is just our concentration after this certain amount of time t. K is rate constant and t is that time. Note, you can rearrange this equation. You can rearrange it, and when you do, because recall the natural log of anything divided by something is the natural log of this minus the natural log of the denominator. So natural log of A naught minus natural log of A equals KT. Rearrange that, we find natural log of the concentration of A equals negative KT plus the natural log of the concentration of A naught, or Y equals mx plus b. This is the equation for a line. So what you'll notice as if we were to graph just the concentration of A versus time, as we saw before, this gives us this type of curve where the reaction is quick at the beginning and slows down towards the end. But if you then, instead of the concentration of A, take the natural log of the concentration of A, natural log of the concentration of A versus time, you get this straight line. A straight line where the y-intercept here is natural log of the concentration of A naught. And so this is one way, if you're in the lab, that you can determine if you've got a first order reaction. Take your data like we have done before, way at the beginning, a couple videos ago. Take your data, graph the concentration of A versus the time, see that it looks like this, then take the natural log of those concentrations of A, and graph natural log of A versus time. If you get a line, a linear plot, then that tells you it's a first order reaction. All right, so let's look at an example. Let's do some math. Everyone wants to do some math. The conversion of cyclopropane, which is this molecule right here, to propene, this molecule right here, is first order. No, we're told it's first order. And here's the rate constant, 6.7 times 10 to the negative fourth per second, second minus 1, at 500 degrees Celsius. So we're given this reaction, and we're given that rate constant. Let's see what the question is. Uh-oh. Earthquake. So the question is, and I've rewritten the rate constant up there so remember it. 3 questions. Awesome. Don't you love it when you can ask 3 questions in the same problem? It's triple the fun. If the initial concentration of cyclopropane was 0.25 molar, what is its concentration after 8.8 minutes? Okay, the reaction started. You started the reaction with 0.25 molar cyclopropane. 8.8 minutes after the reaction started, what is the concentration of the cyclopropane? What's the concentration of your reactant still? Question 2, how long will it take for the concentration of cyclopropane to decrease from our starting 0.25 molar to 0.15 molar? How long will it take to do that? And third question, how long will it take to convert 74% of the starting material? That third question there is a little bit tricky. It's not too bad once you get the terminology, but we'll look at that a little more closely when we get to solving that one. So let's answer these 3 questions. First question, the initial concentration of cyclopropane is 0.25 molar. What is its concentration after 8.8 minutes? Note, well, let's see, what data are we given? We're given an initial concentration. We're given a time here. We've already got a rate constant. Oh, if only there were some sort of mathematical equation that related those 3 things. Here it is. The integrated rate law, the integrated rate equation. We know that the natural log of the initial concentration that we were given divided by the concentration at time t, that's what we're after, equals k, the rate constant, times that time, which is 8.8 minutes. Now, there is a bit of a problem. Note that the rate constant is in units of seconds per seconds, and this time here was given 8.8 minutes. So we can't just quite plug everything in there, but pretty close. Natural log of the initial concentration over A, which we're after, equals the rate constant times 8.8 minutes times 60 seconds per minute. You have to convert the minutes to seconds by multiplying by 60. No great feat of engineering there. All right, so When you do that, you will find that the natural log of 0.25 molar over A equals 0.354. The result of this math is 0.354. But now we have a natural log, and how do we get rid of a natural log? With a natural chainsaw, otherwise known as E. Remember, E to the natural log of anything equals that thing. E to the natural log of anything equals that thing. So this part right here works out to be just 0.25 molar over A. And this is E to 0.354. Just plug that into your calculator. And when you do that, E to 0.354, you get 1.42. So here we've got A in the denominator, so general math here, multiply both sides by the concentration of A. We get 0.25 molar equals our E to the 0.345, our 1.42, times concentration of A. Math tells us the concentration of A is 0.18 molar. So when this reaction is going, after 8.8 minutes, our concentration of cyclopropane, our starting material, has dropped from 0.25 molar to 0.18 molar. Okay. Second question, how long for the concentration of cyclopropane to decrease from 0.25 molar to 0.15 molar? Well, same equation. We just have to put in the different variables. Natural log of A naught, 0.25 molar, over A, 0.15 molar, which we're given, equals our rate constant times the time. So we don't even need to bother with our E to anything here. Just do the math, 0.25 divided by 0.15, take the natural log of that, divide it by 6.7 times 10 minus 4th, and we get the time is 7.6 times 10 to the second seconds, which is 13 minutes. All right, note on an exam, if the question is how long will it take for the concentration to drop, if you left the answer 7.6 times 10 to the second seconds, that is perfectly acceptable. That is a unit of time. However, occasionally the question will ask how many minutes for this process to occur. Then it is mandatory that you convert it into minutes because that's what the question asked. But the way this question is worded, time, you could have used it in seconds, or you can convert it to minutes. Either one is fine. Realize that if the exam is multiple choice, you might have to convert it to minutes because that's the only right answer, is the one that's converted to minutes. All right, so third question, how long will it take to convert 74% of the starting material? Now this is a little bit tricky because we're converting 74% of the starting material, our cyclopropane. The question is, how much is left? If you've converted 74% of the starting material, how much of the starting material is left? Well, if 74% has reacted, only 26% remains. There's 26% left. And once you get to this point, there's two ways to do this math. One is the harder way. It's not that much harder, but one's the harder way and one is the easier way. Because we need to take the natural log of the concentration of A naught divided by the concentration of A. And we have 26% of that concentration of A remaining. And so what one is tempted to do at the beginning is just this. Take the natural log of our 0.25 molar divided by, we need to find what's 26% of this 0.25. Well, that's 0.25 times 0.26. And when we do it this way, can we see that the 0.25s will cancel out? So, whereas you could do this math, take the 0.25 here and 0.25 times 0.26, you could just put 1 and 0.26. Just any number up here and 26% of it down here since you're doing this division. So that's the easy way. When you say, oh, only 26% remains, just put 1 and 0.26. Makes the math easier here. Equals KT, and working out the math, there you go. All right, so that answers that problem. We will continue on with first order half-lives in the next video.